Now, the more theorems we have in a mathematics course, well, the simpler will life become, because they're useful tools. You will not have to go through the definition and through all the details. So you will have some very powerful tools which will simplify life. Now we'll have three different levels of characterizing compactness. One was at the level of Euclidean spaces, the second at the level of metric spaces, and the last one in general for topological spaces. But for the third part, well, we need one definition. Let us start by doing that. Now let I be a non-empty set, which we'll use as an index set, and script A alpha, alpha in I, a collection of sets. Now, we will say that this family of sets has the finite intersection property if and only if, no matter what finite non-empty subcollection of this collection we take, the intersection of the sets in that subcollection, they will turn out to be non-empty. A is said to have the finite intersection property if, well, and we'll abbreviate this henceforth by FIP, if for every non-empty finite subset E of I, one has intersection of F alphas, alpha in E, non-empty. Now, this is our characterization theorem. Now, one, this will be referred to as Heine-Borel theorem. Now, let K be a subset of some Euclidean space. Our convention is if we do not mention any metric topology on our M, we mean it under the usual metric. Now, K is compact if and only if K is closed and bounded. Well, this will be a very useful theorem because given a set K, to check whether it's bounded with respect to the usual metric and whether it's closed with respect to the usual metric, that will be easy. The second level will have a general metric space. Let Xm be a metric space. And K a subset of that. Now, K is compact if and only if. Now, what we'll do is we will actually consider the sequence versions of these. Now, in Rm, if a sequence is bounded, then it has a convergent subsequence by Bolzano-Weierstrass theorem. But we have seen that that's not the case in general for metric spaces. Now here we will replace that, and closedness here. Now the sequence characterization of closedness was, well, it said it's closed if and only if every sequence in that set, every convergent sequence in that set, well, has its limit within the set. It converges to something within the set. So the combination of them will read as if and only if every sequence in K has a convergent subsequence so instead of starting with boundedness and leaving the existence of a convergent subsequence to Bolzano-Weierstrass, we take it here just as part of the condition, whose limit belongs to K. And this is the counterpart of closeness. Now, what we'll do in the proof of this theorem, I'll write the third statement as well. I will leave the proof of this to you. We will deduce the proof of Heine-Borel from here, and, well, the third one, that will be separate and independent of those. Now, this is for general topological spaces. And again, we take this here. Now, in defining a topology, we took the notion of an open set as our point of departure. But once we know what sets are open, we know all closed sets. So, while equally well, we could have started with closed sets, actually. We could first specify closed sets, and the consistency condition, the yardstick for consistency would be the closed set properties, which we obtain, and then define a set open if and only if its complement is closed. Thus, we expect, well, once a concept, a topological concept is defined in terms of open sets, there should be a counterpart of that in terms of closed sets. So this will be expressing actually compactness in terms of closed sets. Now, K is compact if and only if for every non-empty family C alpha alpha in I. Well, henceforth I will note where I is a non-empty set. I will not write that anymore. When I use this notation, it will be automatically understood that I is some non-empty set, which is an index set, family of closed sets in X. Of course, with respect to tau, I will not write that as well, such that if I take the intersection of these with K, so this will be a family of subsets of cap K, such that this family has the finite intersection property. For every such family, one has that the intersection of C alpha intersection K's over the entire family over cap I is non-empty. So let's start by first noting that by proving that one holds, well, if we assume the truth of two. Okay, so it's a biconditional. Now let us first assume that K is compact. We need to show two things, that K is closed and that K is bounded. Now let's first show that K is closed. But the sequence version of closedness, well, that was, I said, is widely used in showing that a set is closed. Well, let's do that. Well, then we will take any sequence in K which is convergent, that is converges to some point in Rm, and that should imply that that point is actually in cap K. Take any convergent. Well, let me write. Here, of course, K might be empty. Well, if I take any convergent sequence in cap K, there may not exist some such sequence. But if I instead assume that Xn is a convergent sequence in K, well, that will get rid of that logical loop, logical gap. So assume that Xn is a sequence in K such that Xn converges to A for some A in Rm. Now we should show that A is in K. That'll complete the proof of closedness of cap K. But if this is a sequence in cap K, and we know that K is compact, well, 2 tells us that there is a convergent subsequence of Xn whose limit belongs to K. By 2, Xn has a convergent subsequence X sub R sub n whose limit belongs to K. But what do we know about limits of sequences and limits of their subsequences? Well, if a sequence is convergent, then every subsequence is convergent and converges to the same limit. Now, x sub r sub n, that converges to A. Since x sub r sub n is a subsequence of the sequence with limit A. But then this says that A is in K. The limit of x sub r n is in K, thus K is closed. Now, let's show that K is bounded as well. Now, let's do that by contradiction. Let us suppose that K is not bounded. Suppose K is not bounded. Well, then this means K cannot be the empty set. The empty set is bounded. So, K is not empty. Since we have in mind using statement 2 in proving that K is bounded as well, let's try to construct a sequence using the unboundedness supposition such that it has no convergent subsequence. Now, well, for that, we can start by taking some x1 in K as the first term of that. So, x1. Now, any radius would do, but in such cases, we take usually the radius to be 1. Let us take a one ball about x1. Is it possible that K is entirely contained in this one ball? Well, this one ball is bounded. Any subset of that is bounded. If K were contained within this one ball, it would be bounded contrary to this supposition. So it will have some point outside, such that the distance from x1 to x2, the usual distance, that will be larger than or equal to 1. So I can take that as the second term of my sequence. Let me first do it. Since K is not bounded, K is not contained in B1 ball. This is the usual distance. I will not write that here. So, pick some x2 in K, but not in B1 of x1. So, the distance between x1 and x2, that will be larger than or equal to 1. Can I continue this process? Yes. Continuing would mean I will take a one ball about x2. I will take the union of these. By lemma, what do we know about the union of two one balls, that will be bounded. So K will not be entirely contained in the union of these. Thus, I can take a third point in K, which belongs to neither of these balls. But what will the property of X3 be? Its distance from X1 will be larger than or equal to 1, from X2 as well. But instead of doing that, let's do it formally by induction, which means the induction assumption, this was the basic step. Now assume that for some natural number n in n, we have constructed x1 up to xn in K, such that no matter what two terms, what 2 points from this n-element collection I take, the distance between them is larger than or equal to 1. Such that for all ij in 1 to n, with I different than j, we have the xi xj that's larger than or equal to 1. The question now is, under this assumption, can I add one more xn plus 1 from cap k, such that its distance to all the points already chosen is again larger than or equal to 1. But for that, now, we know that the union of the one balls of xi's, I from 1 to n, is bounded by a previous lemma. So, K is not contained in this union. Because if it were, then K would be bounded, and that would contradict our supposition. So pick xn plus 1 in K such that it is not in this union. But then, the distance of xn plus 1 from each xi, when I runs from 1 to n, that will be larger than or equal to 1. Then, for all I in 1 to n, the xn plus 1 xi, that will be larger than or equal to 1. But that completes our construction by induction. Thus, by induction, there is some sequence xn in K such that for all ij in n, no matter what 2 terms in this infinite sequence I take, if they are different than each other, we have dxi, dxj larger than or equal to 1. Now, this sequence should actually contradict the condition in here. That is, that every sequence in K has a convergent subsequence whose limit belongs to K. Well, we have assumed that K is compact, thus by 2, that right-hand statement, that must be true. As K is compact, by 2, and this xn is a sequence in K, it has a convergent subsequence whose limit belongs to A. Xn has a convergent subsequence x sub r sub n such that x sub r sub n converges to A for some A in K. We will now show that that's not possible because of this condition. Okay, let's do that. Now, set epsilon equal to 1/2, which is positive. By definition of convergence, there should exist some point in this sequence such that every term beyond that should have a distance from A which is less than 1/2. That's just by definition of convergence. Now, there is, say, some L in N such that for all N larger than or equal to L, we have the distance of x sub r sub n from A less than epsilon, which is 1/2. Now, on the other hand, let me just take two different n's beyond L. Well, I can take that. R sub L, that's different than, well, just let me take the next one, R sub L plus 1. Implying that by this condition here, I take I as R sub L, J as R sub L plus 1, they're different, then their distance has to be x sub R sub L and x sub R sub L plus 1. They should have a distance between themselves which is larger than or equal to 1. D x sub R sub L, x sub R sub L plus 1 is larger than or equal to 1 by construction of the sequence xn. But now, so we can combine actually this convergence condition with this. We have the following. One is less than or equal to the x sub R sub L, x sub R sub L plus 1 on the one hand. But on the other hand, I can use this and this, since L is larger than or equal to L, and L plus 1 as well, well, they also should satisfy this. Their distance to A separately, individually, should be less than 1/2. So this will be less than or equal to d x sub R sub L A plus dA x sub R sub L plus 1. But this is less than 1/2. This is less than 1/2. So this is both larger than or equal to 1 and less than 1, which is a contradiction. The reason why we took here 1/2 is, well, we took 1 here, so that's half of that. We use the triangle inequality, so we have 2 1/2s here. So K is bounded. So that takes care of half of this. If K is compact, we have shown that it's closed and bounded. But let's show the converse as well. Any questions here? Let me use this part. Conversely, assume that K is closed and bounded. We will not show that K is compact, but we can again use 2 in doing that. Well, instead of using directly the definition of compactness, we can use this characterization. If we now show that every sequence in K has a convergent subsequence whose limit belongs to K, then that will imply that K is compact. Moreover, assume that Xn is a sequence in K. But before I proceed with this, let me draw your attention to the following fact. In this first part, we just used the metric properties of D. Nothing peculiar to Euclidean space. Thus, well, we can generalize this. Well, we can say if in a metric space, if K is compact, then the set is closed and bounded. Just replace D by M here everywhere, because we just used that D was a metric, nothing further than that. But here, assume that Xn is a sequence in K. Now, if we use the characterization in 2, we should show that Xn has a convergent subsequence whose limit belongs to K. Well, in general, K being closed and bounded does not imply, in general, in a metric space, does not imply that this sequence, any such sequence, will have a convergent subsequence. It may or may not. Well, it does not, but it may or may not. But what do we know in Euclidean spaces? If a sequence is bounded, then it has a convergent subsequence. Since K is bounded, the terms of this form a set which is in K, so that's bounded as well. Now, Xn is bounded, and thus has a convergent subsequence X sub R sub n by Bolzano-Weierstrass theorem. Now, X sub R sub n converges to A for some A in Rn. But so far we only have used boundedness. We know K is closed as well. So the limit of every convergent sequence in K must belong to K. Since K is closed, A belongs to K. So, well, let me write it once more. Every sequence in K has a convergent subsequence whose limit belongs to K. Thus, by 2, K is compact. So that completes the proof of Heine-Borel theorem given the characterization of compactness in metric space.
So most probably in Bolzano-Weierstrass theorem, they use supremum principle there.
Yeah.
Isn't it? You should use supremum principle in Bolzano-Weierstrass theorem. Because if not, I mean...
No, but that's the whole thing, actually.
Because we prove 0, 1 is compact, it would be easy.
Yeah. Well, now, once we have this, of course, closed and bounded, 0, 1, the closed interval 0, 1 is clearly closed, it's bounded as well, thus it's compact. But Bolzano-Weierstrass theorem is true. Well, its truth is based on the supremum principle. So, well, this also shows the more theorems we have, the simpler things become simpler, okay? Okay. We'll come back to the simplicity and usefulness of this theorem, and, well, then, well, see, can we find some version of that which is true in metric spaces as well? But just go into that after we finish the proof of this. Okay. Now we have the third statement. It's again a biconditional, but the proofs of both parts are similar. I'll go through the proof of one part and leave the proof of the converse to you. So assume that K is compact. Well, in order to show that the right-hand statement is true, let us take any non-empty family of closed sets in cap X such that this has the finite intersection property. Moreover, assume that C alpha in I is a collection. Well, let me write non-empty as well. A non-empty collection of closed sets in X such that C alpha intersection K, alpha in I, has the finite intersection property. Well, if this implies that the intersection of these sets over the entire index set, over the entire family is non-empty, then the proof of this part, of the only if part of this statement, that will be completed. Let's proceed by contradiction. Suppose this intersection, C alpha intersection K, alpha in I, is empty rather than non-empty. This should lead to a contradiction if the statement is true. But here we have just a definition of compactness. For general topological spaces, well, that's the only thing we have at hand. So, using this supposition, let us try to get an open covering of the set K, which will not admit any finite subcovering. But since we have assumed that K is compact, that will be the desired contradiction. Well, these are all closed, so their complements are open. Consider the collection G X minus C alpha, alpha in I, of open sets. Now the question is, will this be an open covering? What does it mean for this collection to be an open covering of K? Well, any point in cap K should belong to the union of these, thus to at least one of these, to some x minus c alpha, to x minus c alpha for some alpha. Okay? Now, assume that x is in K. But x in K, together with this supposition, what does that imply? Well, x cannot belong to C alpha for each alpha. If it did, it would belong to C alpha intersection K for each alpha. It would belong to this intersection, and this would not be empty. Then, x does not belong to C alpha for some alpha in I. But that means it belongs to the complement of C alpha. That is, x belongs to x minus C alpha. So, x belongs to the union of x minus C alphas, alpha in I. Thus, G is an open covering of K. What do we know about K? It's compact. So this G has some finite subcovering for K. Let me write that in terms of a non-empty finite subset of this index set. Since or as K is compact, there is some non-empty finite subset E of I with K K is contained in the union of X minus C alphas, alpha in E. I'm sorry, alpha in E. So that's crucial. This is the finite subcovering. Well, that means K will be contained in here. What do we expect that to be in contradiction with? With the finite intersection property. But as this collection has the finite intersection property, has the finite intersection property, well, the intersection of C alpha intersection K's when alpha is in E will be non-empty. Well, then pick some X from there. Will it contradict this? Yes. X is in K. X is in each C alpha for alpha in E. So X does not belong to none of the complements of C alpha when alpha is in E. Then X is in K, and for all alpha in E, X is in C alpha. That is, X does not belong to X minus C alpha for all alpha in E. Contradicting that, X is in this union, K is in this union. K is in the union of X minus C alpha, alpha in E. So, the intersection of C alpha intersection K, alpha in I is non-empty. This supposition, that must be false. Converse, exercise. So that completes what we wish to do with this theorem. Okay? Any questions about the proof? Next hour, we will get back to the especially simple statement of Heine-Borel, and we'll try to see what can be done with that if we wish to modify that so as to make it fit to the context of general metric spaces. But let's have a break first.